For this STEMbite, I like to figure out how old this big, beautiful tree is in our yard. Usually the way you think of measuring the age of a tree is to cut it down and then count up all the little rings inside. Needless to say, I'd rather not cut this down. I do, however, have another tree that we cut down not too long ago. So I wonder, could I count the rings in this tree and then use that information to figure out how old that tree is? So here's what I'm thinking. If I count all these rings and then measure the circumference all the way around this tree, maybe I could find a relationship between the circumference and the number of rings. Now you can see some of these rings are thinner, some of them are thicker, depending on whether it was a good year or a bad year while the tree was growing. But presumably, since this tree's in the same yard as that tree, they experience the same weather, so I'd guess the average ring size would be about the same. Okay. 1, 2, 3, 4. So we got 75 rings, so this tree's about 75 years old. Let me check the circumference. This is going to be a rough measurement. It's like 90 inches. 90 inches divided by 75 years, about 1.2 inches per year. Now that suggests that each year, this tree gets 1.2 inches bigger around. But it makes me wonder, I mean, this tree is already way bigger, so I would assume each year it gets bigger and bigger around, that I can't just use an average number like 1.2 inches a year. Like, here's a brand new baby tree. It's not going to get 1.2 inches all the way around in its first year, I don't think. And by the time it's a giant, I gotta believe it's getting more than just 1.2 inches of additional circumference. But I'm trying to get an estimate here, so let's check. Let's see here. How do I do this? Oh dear, tape measure's not long enough. So if I bring this around to there, 166 inches divided by 1.2, 140 years old. Wow, that's an old tree. This question about circumference is still bothering me though. Let's say I want to measure the circumference of this exercise ball. I could run a string all the way around the equator. Now let's say this ball got a little bit bigger. Like, let's just say it got 1 centimeter more in its diameter. The question is, how much more string would I need to go around the ball then? Just to make it easy, let's say the ball has a radius of 10 centimeters. Then its circumference is 2 times pi times 10. If I add 1 centimeter to its radius, like having the string go up like this, the new circumference would be 2 times pi times 11 centimeters. So the amount of string I'd have to add is just the difference in the two circumferences. 2 times pi times 11 centimeters minus 2 times pi times 10 centimeters. Well, that's just 2 times pi times 1 centimeter, the amount of radius that I added. So if I add 1 centimeter to the radius of this ball, I only need to add about 6 centimeters to the string, and it could go around the whole circumference. But here's the crazy thing, right? In my answer, it didn't matter how big the ball was. Like, what if this ball was the whole Earth? And I ran a string all the way around the Earth, and back the other side. Now the radius of the Earth is like, probably 1,000,000 centimeters, right? And if I want to increase the height of that string by 1 centimeter, you could say, well, how much additional string would I have to have so that that string can now go all the way around the Earth 1 centimeter higher? Well, we would do the exact same calculation and we'd get the exact same answer. To move that intercontinental string up 1 centimeter around the whole world, we'd only need to add about 6 centimeters to the string. That can't be true. Son of a gun. This is insane. Check the math yourself. It's true. STEMbite.